Okay, hello everybody. Welcome to this month's and the first of the fall section, Chalmers AI for Science seminar series. This is a seminar series where we are inviting people at the interface of natural sciences and AI and machine learning to give a presentation about their research. And we are particularly interested in highlighting excellent young researchers that are in the early to medium phase of their career to present their research. And today we have Perdikaris from the University of Pennsylvania. He is an assistant professor there at the Department of Mechanical Engineering and Applied Mechanics. He has a PhD in Applied Mathematics from Brown University. And he has, prior to joining Penn, been a postdoc at the Massachusetts Institute of Technology, where he was one of the pioneers of this physics-informed neural network method that has been very broadly adapted now throughout the science and engineering communities. He has received already numerous awards and grants for his excellent work, and we are very much looking forward to hearing his presentation today. So please, Pardis, take it away.
Great. Thank you very much, Simon, for the invitation and the nice introduction, and thank you all for tuning in. It's a great pleasure to share some of our recent work with you today. By the way, feel free to interrupt me if you have any questions at any point, or use the chat window to type your question. So today I'll be presenting some recent work with PhD students, postdocs, and collaborators at Penn on supervised and physics-informed learning in function spaces. And specifically, one of the key goals of this work is to build surrogate models for continuum systems and being able to build fast emulators for partial differential equations. So let me start with a motivating application setting. I know that many of you have been doing fantastic work on using machine learning techniques for molecular modeling. And you might recognize some of the similar challenges that I will present now for continuum systems and PDEs. So consider the case that you want to use simulation-based tools for design optimization of some complex system, let it be a molecule or in this case, a rocket. So in this setting, you will have a collection of variables that you're free to choose from, a collection of design inputs that could be a vector of variables or sometimes even functions. And then associated to each design choice you make, you can observe a system state by simulating some governing system of equations. So in the context of the examples I'll be presenting, those governing equations typically will be a system of partial differential equations. So U here will be denoting the input design functions or control functions. S will be denoting the associated system states that you obtain by solving the PDE. And this calligraphic operator N at the top left of the slide will essentially describe the PDE operator. So the solution to this PDE will be a continuous function of space and time coordinates, X, Y, Z, and T. And then based on this solution, we will design an appropriate cost functional that will measure the performance of a given design. And now the goal is to explore the design space that often can be really, really high dimensional and try to find candidate solutions that maximize or minimize the target cost functional. And this procedure typically will be limited by the cost of the underlying simulation. So oftentimes we are limited by our computational budget, and we can, oftentimes the simulations might be very complicated and expensive, as you see here, involving high-speed fluid flows and shocks and turbulence. They require really, really high resolution to resolve the underlying physical mechanisms. And then, you might start exploring the design space, either guided by gradient information, if you can also can simulate adjoints, or using techniques like Bayesian optimization on reinforcement learning. And then at some point, you hope that you identify some design candidate that is good enough. Typically, it will be really hard to sort of guarantee convergence to some global optimum here. And as I mentioned, the main two challenges here are related to the cost of solving the governing equations. So for systems of realistic complexity, that could take hours or days or weeks, even on supercomputers, and also the dimension of the input design space. So if the possible universe of choices that we can choose from is large, then inevitably we will need to evaluate the system many, many times in order to identify and sufficiently explore the design space to find good solutions. Now, the second bullet is something I won't talk much about in this talk. And again, I mentioned earlier that techniques like Bayesian optimization on reinforcement learning can be used for enabling the judicious exploration of the design space. Today, we'll focus more on how we can alleviate the cost of solving the governing equations. And we'll try to use machine learning techniques to essentially learn a map from the input variables to the associated system states that are the outputs. And we'll try to learn that map in the classical machine learning setting, given some data pairs. In the next few slides, I'll try to motivate the setting of building models that can accommodate functional data, because in the most general setting, these inputs and outputs, U1, S1 to UN, Sn, will actually be continuous functions. And the main message here is that there is some hope to learn such maps, even between infinite dimensional function spaces, as long as the target output functions, S1 to Sn here, concentrate or live on a low-dimensional submanifold in some ambient function space. So let me first start with a brief review and also introduce notation. So this is a setting that you're all familiar with, but I'd like to illustrate it through a very, very simple example. So we'll be talking about supervised learning. So let's start with a conventional setting that everyone is familiar with, that involves learning a function that maps two vector spaces. So again, in the context of PDE systems, let's think about a two-dimensional fluid flow, and our goal being to predict the velocity and the pressure of a fluid for a given geometry of an airfoil cross-section. So our inputs will be some representation of the geometry. So for instance, you could think of representing the geometry using 32 grid points around the surface. So you have XY coordinates, so a vector in R64. And then correspondingly, you simulate the flow through an experiment. And now you can observe the velocity and the pressure of the fluid around the airfoil. So now your outputs will be some representation of those quantities of interest. So let's say you run some finite difference solver, and now you have the solution evaluated on a grid that has a resolution 128 by 128. And then you have three variables of interest, so U, V, velocity, and the pressure. So now in a supervised learning setting, the setup is that given a collection of realizations of the system, so a bunch of geometries and the associated flow fields around them, your goal is to fit a function that maps vectors living in R64 to vectors living in R49,000, such that you interpolate your training data, or you kind of regress as close as possible to your training data. So this approach will essentially be limited by two key factors. And in this talk, I'll try to motivate why we might want to take a slightly different approach. So first of all, it might look like a daunting task at first. This is an interpolation problem in very high dimensions, but deep learning actually provides tools that give us some hope of actually learning functions in these settings. So depending on the structure of the problem, you can use architectures like convolutional nets or even transformers and try to fit that training data. However, models like this will not be able to accept new measurements or new measurement locations. So for instance, if at test time, now you want to investigate the performance of a new geometry, however, that new geometry is slightly more complicated, and you need to use maybe 58 grid points to represent it accurately. This model will not be able to accept inputs of different dimensions. So it won't be able to accommodate inputs of different resolution. Similarly, if you want to make a prediction at a different grid point that does not live in your 128 squared grid, you'll have to resort to some post-processing or interpolation routines to achieve that. So the message here is that by trying to set up the problem in terms of learning functions between finite dimensional vector spaces, we are completely constrained to our initial choice of discretization. And of course, this is a philosophical question. Should you discretize first, or should you formulate models that can accommodate continuous data? A more practical limitation is that if you choose to discretize first, then you will also be limited by resolution. So for instance, if the physics of the problem require you to really zoom in and resolve fine scales, so for instance, the boundary layer across near the surface of the airfoil typically is a very important region to be resolved in order to accurately estimate quantities like the drag coefficient, then such approaches will be hard to scale because you will need a very, very high resolution. So maybe 128 by 128 is not enough. You might need thousands by thousands, or even in 3 dimensions, it might be even harder. So then the underlying architectures need to become really, really large, and then quickly you run into computational bottlenecks. So now to address these sort of shortcomings, one may think of taking a leap of faith and try to formulate the problem in a more abstract setting, that is supervised learning in function spaces instead of vector spaces. And that goes with the observation that not all data can be potentially represented faithfully as vectors. And in many applications in engineering and physics, we're dealing with inherently continuous quantities of interest that are defined in continuous spatial domains, and they have variation continuously in time and so forth. So revisiting the same exact example from now the function space point of view, you can think of parameterizing your inputs as parametric curves. So that is functions that take some continuous variable in 0, 1, and then map it to the x1 and x2 coordinates of points on the surface of the airfoil. And then similarly, your outputs are inherently continuous variables of interest. So they are functions of space and time that you can evaluate continuously at any point, both the velocity and the pressure components. So now, in a very similar sense, we can formulate the supervised learning problem at the level of learning an operator that maps input functions to output functions. And then our goal, of course, will be now to parameterize this operator to come up with a parametric class and try to fit that class to the training data. Again, now we are not discretizing the data. Of course, as we will see later on, functions are infinite dimensional objects. Eventually, at some point downstream, we need to deal with finite dimensional representations. However, here the model is formulated at the level of a function space. It should be able to accommodate functional data, and therefore it should learn to reason about the functions themselves instead of some discretization of the functions. So formulating an architecture for learning operators that can map function spaces will allow us to accommodate different discretizations and different resolutions, because we're still reasoning about the same operator without having to rebuild or retrain the model. So the key message here is that formulating models at the level of operators will bias this invariance with respect to the discretization and the resolution of the input and the output data. So this is an area that has received quite a bit of attention in the last few years, and you might have seen frameworks like the Fourier neural operator or deep operator networks, typically referred to as DeepONets. We have done also some work on formulating architectures that are inspired by the attention mechanism. So altogether, these frameworks have demonstrated promise. Most of them are also accompanied by universal approximation guarantees. And to some extent, they have been shown to be effective in mitigating the curse of dimensionality, at least in certain cases. And we'll talk a little bit more about that later. And if you're successful to train such models, you might be able to build really fast surrogates that could be up to 3 or 5 orders of magnitude faster in predicting continuous fields compared to classical numerical solvers like finite element methods. And again, because we're formulating models at the level of an operator, we have this built-in property that the model is invariant with respect to the resolution of the training data and can be evaluated continuously at any new query location. Now, some of the drawbacks, this is, again, typical deep learning setting. You need a large amount of training data, oftentimes thousands of labeled examples of input and output functions. And you can imagine that this might be very costly. Oftentimes, again, those simulators that generate the data can be very, very expensive. So in many scenarios, maybe we cannot really afford to generate large volumes of training data. We'll revisit this limitation a little later in this talk to motivate physics-informed approaches or think about inductive biases and data efficiency. And also generalization may be poor in the sense that, if now you are presented with a test function that lives in the tails of your training data distribution or outside of the training data distribution, you might get really bad predictions, and also without a warning. You may not know that this is a bad prediction. And of course, that motivates the need for uncertainty quantification and other aspects to sort of control that aspect. So in the next few slides, I'll try to take a more general perspective of how one can build or parameterize an operator using deep neural networks. So we'll talk a little bit about an approximation framework. And many of those techniques that you see on those slides can actually be interpreted through the lens of this general approximation framework by making different choices for different components of a model. So let me just briefly talk about the general setting. As I mentioned, we will be trying to learn operators that map input functions to output functions. So we will typically have access to a collection of data. So we have observations of input functions that are sampled from some measure over a function space like L2. We have a general nonlinear operator that we don't know, here denoted by G, and that operator maps each function in the input space to a target function in the output space. Those output functions will be distributed according to a push-forward measure, here denoted by G sharp mu. And then calligraphic X will denote the domain, the input domain of the input functions, and then similarly calligraphic Y will denote the domain, the input domain of the output functions. And typically, I will refer to points in these domains as the query points where we want to evaluate those functions. So now, in general, and this goes back to actually work done back in the 90s, one can construct an approximation to this operator G by 3 maps. The first map is referred to as the encoder that receives a continuous function as an input and then constructs a finite-dimensional representation of this input function. So you could think of the encoder being a point-wise measurement functional, that you take an input function, you measure it in m locations, and now you reduce it into a vector in Rm. Alternatively, you could think of taking an input function and projecting it on a chosen basis of wavelet functions or polynomials or sines and cosines, and then retain the m largest projection coefficients. So these are examples of different choices one can make for the encoder. Then the approximator map will be a map between 2 finite-dimensional vector spaces, and essentially we'll try to mimic the discretized action of the operator G. So it will receive a vector in Rm and then map it into another vector space Rn, which I will refer to as the latent space of our model. So vectors in Rn, as we will see later on, will be sort of capturing the latent representation of our model. And then we'll have a decoder whose job is to receive a vector in the latent space and then project it back and reconstruct output functions in the output function space. And then for most of the existing models in the literature, including the DeepONet or the pseudo-spectral Fourier neural operator, this decoder map is a linear map. That is, it acts on vectors beta that live in the latent space and reconstructs functions in L2 by constructing a linear combination of basis elements, here denoted by tau I. And then in different models, you can have different choices. For instance, in DeepONets, those tau I basis functions are parameterized by neural networks. In the Fourier neural operator, they're parameterized by trigonometric polynomials. And you can imagine making different choices. But the key point here is that linear decoding maps of this form essentially are trying to learn a coordinate system in a finite dimensional linear subspace that tries to capture the variation we see in the output functions. So essentially, each of the output functions in our training data set is represented as an element that lives inside a linear finite dimensional subspace inside L2 of Y. Now, there's some really interesting results about constructions like this that date back to the work of Chen and Chen in '95, and that is that models that inherit this commutative diagram and use a linear decoder of this form can be shown to have universal approximation properties. So they can approximate any arbitrary nonlinear operator to the desired accuracy. So now, that kind of partially answers the question of when do we expect this to work. So maybe theory tells you, well, you have a universal approximation guarantee, so this should always work. However, this is not a very useful statement in practice because it doesn't really tell you how big your model needs to be in order, or how large the latent dimension of your model needs to be in order to approximate the target operator with desired accuracy. So it's more of an existence result, but in practice, it doesn't have a lot of value. In order to produce some results that are a little bit more useful in practice, and under mild regularity assumptions, specifically that the push-forward measure has finite second moments, so this relates to some basic regularity assumptions on the operator G, one can actually examine the covariance structure of those output functions and define the covariance operator that acts on functions in L2Y. And this covariance operator, by definition, will admit some eigendecomposition. So you have an infinite collection of eigenpairs, eigenvalues lambda j, and eigenfunctions phi j. And in fact, you can actually prove for models that use linear decoders, and regardless of the modeling choices you've made or whatever architecture you use, such models will be limited by the following fundamental lower bound. So you can actually derive a lower bound in the uniform norm. That's what you see in the bottom left of this plot. Essentially, here you have the risk, the population risk of your approximation error. F is your operator parameterized by these three composition maps, and G is the ground truth operator. And you see that this approximation error will be bounded by below by the sum of the eigenvalues that you have neglected. So remember, the latent dimension of your model is n. So if we truncate the eigenvalue spectrum of the output covariance operator at index n, and we are ignoring the tails of this eigenvalue spectrum, our approximation error will actually be bounded by below by that sum. And what that essentially tells you is that you can expect all this business to work if the covariance operator defined in the output function space has a very fast spectral decay, and then it's reasonable for you to kind of truncate that eigenvalue spectrum early and use the model with like a low or a moderate dimension of a latent space, here denoted by n. Also note that this population risk is actually the loss function that you're going to use for training this model, or kind of a Monte Carlo approximation of this, like an empirical risk version of this. A similar lower bound can be derived in the L2 norm, and that's what you see in the bottom right of this slide. And in this case, another familiar quantity arises, which is the so-called Kolmogorov n-width. And this is a measure of how well a linear subspace can approximate functions that live in the image of the operator G. And again, your approximation error in this L2 norm is going to be bounded by from below by this quantity. So all this basically says, if I am to summarize the slide, that this construction that I showed you, and regardless of the choice of the architecture that you make, you could use trigonometric polynomials like in the Fourier neural operator setting, or neural networks as in the DeepOnNet. This will work as long as your target output functions concentrate and live in a low dimensional linear subspace of L2Y. And that could be the case in many applications, and that's why those techniques have demonstrated success, but it may not be the case in other applications. And a great example of applications where this is not the case is problems, advection-dominated problems or wave propagation problems. And let me give you a very simple example just to motivate and illustrate what the issue is here. So here, let's consider a simple one-dimensional advection equation, basically describes the propagation of a wave in one dimension. So, and what you see here is snapshots, temporal snapshots of the solution of this equation at different times. So you have a wave that is traveling from the left to the right. And what I'm doing here, I'm taking two consecutive snapshots, and then I'm computing the covariance between them. So every entry of this matrix here contains the L2 inner product between the black function that is fixed and then the gray function that is traveling from left to right. And as you see here, the covariance will be zero. The off-diagonal entries will be zero unless those two waves perfectly overlap with each other. So the covariance is sort of a measure of linear correlation between those two things. And to the eyes of this linear measure, those two consecutive snapshots will not be correlated unless they really overlap with each other. Now, if you take the entire temporal solution, so all the temporal snapshots, and you actually run a functional principal component analysis, and you try to plot kind of the empirical spectrum of your covariance operator in this function space, you will see a relatively slow spectral decay. So you will see that in order to capture the variance of this data set, you will need to build a model with a latent dimension that is at least 20, as you see from this eigenvalue decay spectrum, which is a little bit of a paradox because it is evident here that we're talking about a one-parameter family of solutions parameterized by time. So you just have a traveling wave. So those functions, all of them should concentrate on a one-dimensional manifold. However, this manifold will not be linear. So if you were to capture this variability with a linear subspace, you will need a latent dimension of 20, although the actual structure here is one-dimensional. And this is precisely the fact that motivates us to revisit the general approximation framework that I discussed earlier and revisit the assumptions we make on the decoder map. Earlier, we saw that most of those models, the existing models, use linear decoders, and thereby they are able to learn linear subspaces in the target output function space. And that can be easily modified in order to accommodate nonlinear decoding maps that hopefully will give you the ability to learn nonlinear manifolds in the target output function space. So let's see how then we can generalize this and construct nonlinear decoders. And this is a busy slide, but I'll try to walk you through it. What you see in the sketch in the top left is a linear setting that we just described. So you have a latent representation in the beta space. Let's say you have beta 1 and beta 2 latent variables, and the decoder takes a point in the latent space, maps it into a point in L2. So every point now in this output space is a function that is reconstructed as a linear combination of your bases, tau 1 and tau 2, times the coefficients beta 1 and beta 2. So you could think that this construction essentially is trying to learn the inverse of a coordinate chart. So the coordinate chart is a mapping from an open subset in this linear subspace to a latent representation, and the decoder essentially is the inverse of this map. So in a very similar flavor, you can think of generalizing this decoder map to be nonlinear by creating or parameterizing a nonlinear function of those latent coordinates. Now, the dummy argument that you see in tau 1 and tau 2, and also in F on the top right of the slide, this little dot, corresponds to the query point in which you want to evaluate your target output functions. So that would be a dummy variable that, at different query points, you will have to provide a different input there. So in order to achieve or build nonlinear decoders, we can consider generalized decoding maps that will jointly take the latent representation of the model and a query coordinate, and then map those two things to the corresponding output function value. So if you look now at the bottom of the slide, you see the distinction between the linear decoder and the nonlinear one. The linear one, I'll take DeepONet as an example, that constructs output functions that live in the image of the operator as a linear combination of basis elements that are parameterized by neural nets. Similarly, a nonlinear decoder will construct and evaluate those output functions by building a nonlinear map that takes the latent space coordinates and a query point in the output function space, and then return the value of that output function evaluated at that query point. Perhaps the difference between those two models can be better summarized in this slide. So these are the different choices that we will be making. So in the next few slides, I'll show you some numerical results that compare the so-called DeepONet structure that uses a linear decoder with a model that we call NOMAD, stands for nonlinear operator manifold decoder. So the encoding map will be the same in both cases. So we'll take input functions U and represent them using M point-wise evaluations. So the encoding map will take the continuous function, map it into an m-dimensional representation that contains point-wise measurements. The approximating map will also be the same in both cases. It'll take a vector in Rm and map it to a latent space of dimension n using a deep neural network, typically an MLP. However, the decoding map will be different. In the DeepONet case, we'll have another MLP that approximates the basis elements tau I. So now output functions will be evaluated as a linear combination of those basis elements times the latent coordinates, beta I. Whereas in the nomad case, the decoder will be kind of like a black box nonlinear function that receives the latent representation and a query coordinate y, and then return the evaluation of the target output function at that coordinate y. So at the very bottom of the slide, you kind of see the different representations. On the left, you have the DeepONet, where the beta functions and the tau functions are parameterized by two different neural networks, typically referred to as the branch network and the trunk network. Whereas in the nomad case, again, we have two neural networks, one that parameterizes the beta coefficients, basically the approximating map calligraphic A, and then a second neural network F that is a nonlinear decoder. Let me give you a very simple example to illustrate the benefits of using nonlinear decoders. So here's an example where, again, though, the target output functions are going to concentrate on a low-dimensional nonlinear submanifold in L2. And this example concerns with learning the antiderivative operators, so learning the operator that maps forcing terms to the associated solution trajectory of an ordinary differential equation. So let's consider now the case where our input function space consists of cosines of different frequencies, and correspondingly, the output function space will be a space of sines of different frequency. And here, t is the parameter that will parameterize these different frequencies. Now, if you generate a training data set consisting of input functions and output functions, and you take all your output functions in your training data set and perform a functional principal component analysis, you will see again a relatively slow decay in the eigenvalue spectrum. And again, this is an indication that if you were to capture those target output functions using a model with a linear decoder, or a model capable of learning linear subspaces, you will need a latent dimension of at least 10 or 20. And again, that's a paradox because we fabricated this data set in a very similar fashion. And again, this is a one-parameter family of functions parameterized by t. However, those output functions, again, concentrate on a nonlinear submanifold, not a linear one. And again, you can also see that this is not a linear subspace by visualizing the leading three principal components. And you see kind of this spaghetti-like curve that twists and turns, colored by the frequency of the different functions. So each point in this curve corresponds to a different function in our training data set, a different output function. All right, so now we can take this training data set, we can train a DeepONet model, and we can train a nomad model. And now we can have a test data set with a collection of input-output maps and functions. And we can evaluate the relative L2 prediction error average over all the functions in our test data set for the two models, the DeepONet with a linear decoder and the nomad with a nonlinear decoder, and over a range of choices for the latent dimension of our model. And what you see here is about a 1 order of magnitude improvement in accuracy. More importantly, you can see that the model with a nonlinear decoder, even when the latent dimension is very low, even when the latent dimension is actually 1, can give about 10% prediction error, whereas the model with a linear decoder is up to 100% prediction error. So this is a very toy, simple example. A few more examples just to convince you, revisiting the advection equation case that I showed you earlier. Now we have a PDE system, and we want to learn the operator that maps different initial conditions. You see an example initial condition on the left plot. The black curve shows a very simple initial condition that is just a very sharp Gaussian bump. And under the dynamics of the advection equation, this wave is going to propagate in time. So now our goal is to learn an operator that maps different initial conditions to the full space-time solution of the advection equation. And we were going to construct a data set by considering translations of this initial condition. So the same sharp bump, but translated in space. Now, if you construct a data set like this, and again, you perform a functional principal component analysis on the output functions, again, you will observe a very slow spectral decay. That again indicates that you will need a model that, if your model uses a linear decoder, you will need a latent dimension of at least 100 or more to capture those target output functions. And again, this is paradoxical because, again, this is a one parameter family of solutions, again, parameterized by the translation or in the initial condition wave. So same comparison as before, linear versus nonlinear decoder. Again, you see a very dramatic difference in terms of the accuracy of the model, especially when you consider very low dimension for the latent space. And keep in mind that being able to work with models that have a low dimensional latent space essentially gives you much simpler models with smaller parameterizations, lower number of trainable variables, and much faster runtime, both at a train time and at test time. Slightly more interesting example, and again, as you notice, most of the examples are concerned with advection-dominated problems. These are the kind of problems that really have this slow spectral decay and motivate the need for nonlinear approximation techniques. This is the so-called shallow water equation. So that's a vector-valued hyperbolic PDE system that describes the evolution of waves on a free surface. So here the problem is parameterized in the following. We want to learn an operator that maps any given initial condition to the full space-time solution, namely the wave elevation and the velocities. These are the dependent variables. And basically what we have is a drop that we release at time 0 at different locations over the free surface and from different heights over the free surface. And then as the drop lands, it creates those traveling waves that are reflected on the boundaries and create those complex patterns. So again, we're going to construct, similar to before, a training data set consisting of many pairs of initial conditions and associated PDE solutions that we generate using a classical numerical solver. And then we will compare against the two different models at test time over a collection of initial conditions that have not been seen before. Once the model is trained, of course, you can make very, very quick predictions. And in one shot, you can reconstruct the entire space-time solution of this PDE. So very similar conclusion as before. This is a case where we don't really know a priori whether the output functions concentrate on a linear or nonlinear manifold. But again, you see here that the nonlinear model can do a much better job with a much smaller dimension of the latent space. And this is a more thorough comparison of different approaches, including the Fourier neural operator, deep operator networks, the attention-based model that we call LOCA. The main thing to observe here is that NOMAD, the method that I just presented, can achieve competitive performance. However, it results to models and parameterizations that contain an order of magnitude less trainable parameters. This is denoted by d theta here, and an order of magnitude smaller latent dimension n. So you see here the DeepONet and LOCA have a latent dimension of about 400 to 500, whereas NOMAD needs a latent dimension of 20. And that translates immediately into savings in terms of computational cost and training and test time. All right, so let me use the last 5 to 8 minutes just to comment on some limitations. And the one important thing to discuss is the need for data efficiency. So in everything that I've shown and everything you can see in the literature, all these operator learning techniques require a large amount of training data, typically in the order of hundreds to thousands of labeled examples. And one needs to resort to conventional numerical simulators or experiments to generate this training data. So obviously this can be prohibitive for applications where the cost of data acquisition is very high. Now there's 3 main principles for trying to introduce data efficiency. One being observational bias, which is typically takes the form of data augmentation. So data augmentation now in this setting has a different flavor compared to conventional data augmentation techniques you might have seen in computer vision. So here we're dealing with continuous systems and PDEs. So what does it really mean to perform data augmentation? You have to start looking into symmetries and symmetry transformations and Lie groups that leave the solution of the PDE invariant under a transformation. And there's some really interesting works in the literature recently in this topic. The second principle would be to try to carefully design architectures that built in carefully chosen inductive biases. So for instance, equivariance with respect to certain symmetry groups, which again also presents several challenges for continuum systems and PDEs. Maybe you can do that for relatively simple symmetry groups like rotations, translations. This is commonly done when modeling molecular systems. However, with PDEs, you have a large number of symmetries, and designing layers for models in function spaces currently seems quite challenging. And then maybe there's the easy way out, and this is an area that my group has done quite a bit of work, what I call learning bias, which basically says, okay, use architectures with weak inductive biases like MLPs, but then try to introduce penalty constraints during training and additional terms in your loss function in order to kind of impose any physical constraints. So for instance, you can take the outputs of your neural net and make sure that those outputs satisfy a given PDE by minimizing the residual of that PDE given that representation. So I will just focus very quickly on this last bullet, which this is the area that I've done most of the work. And you could revisit everything that I showed you earlier. And this is just a simple example through the lens of the DeepNet model, and actually augment now your loss functions with additional terms that try to penalize the physical consistency of what your neural net outputs. So you will not only try to fit your training data, which is what I call the operator loss, but also you'll have additional loss functions that try to penalize the residual of a underlying system of equations, here kind of described with a calligraphic N operator. And you'll try to minimize that residual at the collection of points that are randomly distributed inside your domain of interest. Interestingly, if you do that, you could actually train these operator models by only knowledge of the equation form itself and the associated initial or boundary conditions. So that is to say, you may not even need to run a conventional simulator and generate paired input and output function, input-output function pairs. So this is quite interesting because you can train these models in an entirely self-supervised fashion. So if you're aware of the framework of physics-informed neural networks, this is a very natural continuation at the level of operator learning and function spaces. And what that really buys you is to build physics-informed neural network models that can generalize across different initial conditions, different boundary conditions, different source terms, or even different domain geometries. So if you're interested in this, I would recommend taking a look at this paper that was published about a year ago, again, in the context of building surrogate models for PDEs. And of course, once those models have been trained, they can be much, much faster than a conventional numerical solver at test time. So of course, there's the offline cost of training, but if you are successful and you've paid that price, then you have a surrogate model that can be extremely fast, orders of magnitude faster than a conventional solver. So this scaling diagram is for solving the so-called Burger's equation. And then you can see the numerical solver is a standard Fourier spectral method, coded and optimized on GPUs, but still is 2 orders of magnitude slower than the surrogate. This is another example, which in the interest of time, I'll skip. The final message I'd like to make is that those surrogate models at the end of the day are fully end-to-end differentiable. So you could think about using them in downstream tasks. Downstream tasks that involves some flavor of PDE constraint optimization. So design, as I showed earlier in my motivating slides, optimal control tasks, uncertainty quantification tasks. So the message here is that if you're able to train a neural operator, then you can really quickly query it at test time. You can differentiate, you can backpropagate gradients all the way to the inputs. And now you have gradient information that can guide the minimization of some cost functional for optimal control or design. So let me just conclude. There is also a lot of underlying challenges that I'd be happy to talk about later on. So there's a need for designing more specialized architectures and training algorithms for these systems. We've done a lot of work trying to address some of those open challenges that arise in the context of physics-informed neural networks, but are also inherited by this physics-informed neural operator setting. So let me just conclude with a very simple example of using a trained neural operator that learns how to map different shape geometries to the associated solution of the Stokes PDE that describes how a viscous flow propagates around an object. So now, once you have that surrogate, you can use it for an optimal control task that asks the question, what is the optimal shape that minimizes the dissipated energy or the drag around the obstacle? And you can see here, in fact, creating those animations was more time-consuming and expensive than actually solving the problem on a laptop. Once you have that surrogate, in a matter of seconds, you can actually tackle this type of PDE constraint optimization problems using gradient-based optimization techniques. So with that, and just to have some time for discussion, let me just conclude. I am appending here some references related to what I presented today, some additional animations of systems that we've worked on. There's certain challenges arising when we're dealing with more sensitive systems that may exhibit chaotic behavior. These are scenarios where there's a really pressing need for accuracy, because when you're simulating such dynamical systems, small errors in the prediction can accumulate very fast and throw you towards the wrong direction. So our work is really focusing on trying to address some of those challenges and create more accurate and more reliable deep learning tools for simulating PDEs and continuum systems. So thanks again for tuning in and your attention, and I'm looking forward to your questions.
Thank you, Pardis, for an exciting talk, a very thorough and great introduction to the topic for, I guess, a lot of people who are not deeply familiar with all the work, excellent work that you've been doing and the context in which it fits. I think it's a very nice example here at the end with how you use these methods in the end in the design application. That would actually have been my question. How could you actually use them in sort of a practical setting? And I think you make a very nice illustration here of this at the end. So maybe before we take any questions from the audience, I'd like to ask, so you point a bit towards some of the limitations, for instance, the problem of formulating neural network architectures that work on function spaces that encode, for instance, these equivariances and invariances that you're interested in encoding in PDE. So where do you see that we go from here? I guess there's a huge space, a huge area of math that potentially could be fleshed out here to build these systems. Mm-hmm. Because I mean, from speaking to mathematicians in this area, they always say, well, this stuff has been solved for many years and there's not really a problem. So where do you see this? Do you see this mainly as an engineering problem that it needs to be implemented and deployed? Or do you see this, that there are some fundamental problems that need to be solved?
That's a great question. I think from a practical standpoint, and going back to this diagram, right? So one of the key components of this diagram is this approximating map, which we should be fairly comfortable with, because this is a map between two finite dimensional vector spaces. And that could be a good place for trying to build equivariances. So we can really leverage all the fantastic progress in this space in building conventional deep learning architectures with equivariant layers and try to inherit some of those advances in building approximator maps that have those equivariance properties. Of course, there's the two additional elements here. If you're thinking about approximations in function spaces, the encoder and the decoder. And obviously, these are two additional places where one can think about introducing structure. But yeah, the concept of building equivariant architectures in function spaces, I think it's still at very, very early stages. I haven't really seen much work. The immediate first step is to really use existing advances and try to build approximation maps that have equivariant layers. Of course, we have to decide, what are the symmetry groups and how we can build equivariant layers around those symmetry groups, which may not be entirely trivial for PDEs. But I think, yeah, that's a kind of crucial and exciting area, but also quite challenging because, the math is fairly complicated in function spaces. And it might turn out that the complexity of doing so is actually pretty high from a computational standpoint. So yeah, my answer is relatively incomplete, but certainly that is an area that is very exciting and hopefully we'll see contributions in the future. Again, my work mostly focused on the kind of the easy way out, which is, soft constraints in the loss function.
Absolutely. I think that it's good to be pragmatic with these things, but we have a question from, and thanks for your answer. We have a question from a member of the audience. I'll ask him to unmute.
Yeah. Hi, thanks a lot for this nice talk. So the last point that you mentioned, the soft constraints. So I mean, I've been working on something similar, and one problem that came up was soft constraints don't exactly implement the physics of the problem. So for example, I will link one of the recent works that I worked on where you want to say that you have a certain physical process and a certain constraint has to be met. Let's say that the matrices that you extract out of this whole model should be orthonormal or something like that. If you give soft constraints to the loss function, you are never guaranteed. It's always in some epsilon term. So what we found actually was a very interesting way where so there are multiple ways to go remedy this without soft constraints. You could do a projection. So you could take and find the closest, physical object close to this that has some cost, or you could, as you mentioned, build it in the architecture itself. So you say that I will, have a decomposition and learn only those parameters that strictly always live within this constraint. But I also discovered a recent other technique, which is manifold learning. So optimization on a certain manifold, where you let everything be unconstrained. But what you do is when you take gradient descent or gradient update steps, you kind of retract to a manifold which you know. Do you have any and this was extremely effective for one of the works that we try to do. Do you have any comments on these manifold learning and what could be a potential problem, or is it something that's not explored so much?
Yeah, I think that's a great question, and you're raising a really interesting point. So if I were to rank, I would say, my ideal way to go would be to really build those constraints in the architecture. If that is too complicated or infeasible, then you have to resort in one way or the other to optimization tools, right? Either formulate the optimization problem and do gradient descent on a manifold. And I guess the challenge here would be whether you can, find the right Riemannian metric, and there's some computational complexity associating with constraining your optimization trajectory to always stay on the manifold. And then going all the way to the more generic approaches where you just do vanilla gradient descent, as you see here, and you introduce these additional loss functions, which also introduces a lot of complexity and challenges in actual solving the optimization problem. So those different terms can have different magnitudes. There's an interplay. You need to weight them with different weights, and it's not entirely straightforward how you make those choices or whether there is effective automated ways for doing this. I don't have a lot of experience with gradient descent on Riemannian manifolds. I've seen some interesting work, but I haven't really seen much in the context of physics-informed learning with PDEs. So if you do have something to share, please send it my way, and I'd love to take a look and discuss more.
Yeah, I just shared it. I mean, it's a simple problem that we use neural networks and everything. I spent half a year doing this, and then when I discovered this really nice, beautiful mathematical way to do it, I was like, why are more people not looking into it? Maybe there's some problem with it. Mm-hmm. So can I ask one more question, Simon?
Absolutely. Go ahead.
If there are others waiting, then I can take it later.
No, you can shoot. That might inspire some more questions. I also have one, but I can wait.
Okay. So, I mean, I guess this is the open question, like the accuracy and uncertainty estimates. So whenever, for example, like you do this kind of simulations, collect data, even if you don't do a simulation, let's say it's an actual experiment and you collect data from an actual experiment physical system, to trust these systems, it's a bit of a problem. So there was one paper which showed that you could solve the three-body problem, or you could basically train on trajectories of the three-body problem and predict trajectories of the three-body problem. We use this in a course now, but of course you cannot get uncertainty estimates on these, and it's not so accurate and stuff. So like the question is that there are these new Bayesian neural network ideas that are coming up. I haven't worked so much on this, but what do you think? Like, is that something that's a solution, or there's like a, clear mistake there to go that way? So I was just wondering.
Yeah, I think there is some interesting and maybe orthogonal directions in dealing with this. The accuracy, of course, is a very important issue, and it becomes particularly important when you're dealing with systems that are very sensitive, multi-scale, chaotic behavior. And again, these are the cases where making small prediction errors, those errors are going to accumulate very fast. And unless you're extremely accurate, you're going to predict the wrong thing, basically. So in this setting, it's still kind of hard to see how those deep learning tools can be successful, because they cannot really compete with the accuracy of classical numerical solvers. So maybe that suggests the different synergy in terms of using those deep learning tools to improve classical solvers. So for instance, if you're able to build a neural operator and that can give you a crude but maybe inaccurate prediction of the solution, why don't you take that solution and try to use it to build better preconditioners for linear solvers and accelerate, your classical numerical method in that way? So I think there's still a margin to accelerate the classical solvers through this deep learning augmentation and make them even, 10 or 100 times faster. Now on the, if we are accept that the deep learning methods will never reach the accuracy and the convergence guarantees that classical solvers have, then yes, there is certainly a need for uncertainty quantification. I think, Bayesian inference for neural nets, it's still not like a closed topic. Like, it can be very computationally expensive. You might, there's complex posteriors in high dimensions. It's not a straightforward thing to deal with. And even if you get some uncertainty estimates, how reliable and how well calibrated those uncertainty estimates are is unclear. We've done some work on using ensembles. I guess this is one simple way of trying to extract uncertainty. And indeed, you can see that for those test examples that live outside of your training data distribution, you can get, the predictive uncertainty can give you a flag of whether you should trust that prediction or not. So at the very rudimentary level, I think they are important to have at this stage. And indeed, they can sort of detect those out of distribution samples that can lead to inaccurate predictions.
Okay, thank you for a very thorough answer. I think in the interest of time, I think we'll end it here. Thank you, parties, for a very interesting and great presentation on your work. And thanks to the audience for a lively discussion. I know there were only 2 people who were involved in the discussion, but we want to respect the time of parties and let them go now. So thank you, and have a nice day, parties, and thank you all for showing up.
Yeah, thank you very much, everyone. Take care.